Okay. So, like I said, 9.3 is inferences for correlation and regression. So the first thing, I'm just going to show you the difference in the notation when it's a sample versus when it's for a population, okay? We kind of started to talk about this the other day. All right? So I'm not going to write the title again because I told you what it was. All right. So for a sample, we know it's statistic. Each of these are statistic versus when it's a population parameter. Okay, so the first one is R. For a population parameter, it's called rho. It's the Greek letter that kind of looks like a P. It's called rho. Then we have A, whereas if it's a population parameter, again, we use Greek letters, so it's alpha. When we have B, for population, it's beta. And for the linear, the least squares line, it's y hat equals A plus bx. So in this instance, it would be y equals alpha plus beta x. So over here with the population parameter, what is your slope? Beta, good, thank you. And your intercept is still the A, but in this case, it would be alpha, all right? Don't forget, what is R? What's R represent? You've been calculating it, but you don't know what you're finding? That's
Like
not
how
good.
strong the correlation is.
Good. How strong is the linear correlation, right? Between X and Y? Is there a linear relationship between X and Y? So rho would be the same thing. Whereas R squared was how close the line fits your data, remember? Okay. So we're just going to jump right in. Requirements. For statistical inference. To make inferences regarding correlation and linear regression, we need to be sure that A, the set XY of ordered pairs is a random sample from the population of all possible such XY pairs. Okay, and B, this is a big requirement, okay? I mean, it's quite a bit of writing. I was trying to shorten it, but I don't know. I couldn't come up with a way, sorry. For each fixed value of X, the Y values have a normal distribution. all of the y distributions have the same variance and for a given x value, for a given x value, the distribution of y values has a mean that lies on the least squares line. So all of the y distributions have the same variance, and for a given x value, the distribution of y values has a mean that lies on the least squares line, okay? And we assume that for a fixed y, each x has its own normal distribution. Just listen to me on this part, and then if we need to, we can write it down. We assume that for each fixed y, each x has its own normal distribution, and in most cases, the results are still accurate if the distributions are simply mound-shaped and symmetric, are approximately equal. So we still want it to be mound-shaped, but it doesn't have to be perfectly normal. That's just what it's saying, okay? So let's talk about testing the correlation coefficient. First, we need a theorem before we can jump right into that. Theorem 9.1 says, let R be the sample correlation coefficient computed using data pairs x, y, and R is computed the way we did in section 1. Okay, I'm not going to rewrite that whole formula. You've got it in your notes. All right. So once you have R, the sample correlation coefficient, then we let H sub O, the null hypothesis, be, and Y have no linear correlation. Now, we're not going to write it out like that. So in other words, rho equal to 0. That's what we're actually going to write. But I wanted you to understand what rho represents. It's the strength of the linear correlation, right? So we're saying there is no linear correlation between the two. So what do you think the alternate hypothesis could be then? Say it, Matthew.
There is no, oh, I lied. Rho's not equal to 0.
Okay, that's the third choice. Yeah, rho is not equal to 0. We could say rho is greater than 0, right? So it does have a linear correlation. We could say rho less than 0. So it would have a negative correlation, right? And then we could say what Christian said, which is rho does not equal 0. Don't forget, this is a right tail test, left tail test, two tail test, remember? Once you've set up your null and alternate hypotheses, the next step then is the conversion of R to a student's t-distribution. And the way we do that is t equals R times the square root of n minus 2 divided by the square root of 1 minus R squared with degrees of freedom equal to n minus 2. What is n? Did someone say it? No? Good, number of sample data pairs. It's the number of sample data pairs. And we know they're x, y, right? One thing I do want to point out, n has to be greater than or equal to 3. I want you to think about if n were equal to 2. What would that mean? We'd have 2 points. So if you only have 2 points, how's that line going to fit? Perfectly. If there's only 2 points, we use that to come up with the line. The line's going to pass through both of them. It has to, right? So you need at least 3 points for this, okay? That's why you want n greater than or equal to 3. All right, any questions on that? No? So how to test it? How to test rho, which is the population correlation coefficient. The procedure. 1, use the null hypothesis where rho is equal to 0. And then your alternate hypotheses, could it be rho greater than 0, or rho less than 0, or rho not equal to 0. So we're going to state those. And then the other thing we need to do here, we need to state the level of significance. So in most problems it's given. If you are given an option, you would have to state using a 5% level of significance or 1%, okay? So once you do that, step 2 then is to obtain a random sample of n greater than or equal to 3 data pairs. And compute, once you have your sample, and then you compute a statistic. Which is t equals r times the square root of n minus 2 divided by the square root of 1 minus r squared, with degrees of freedom equal to n minus 2. Okay? All right, the third step in the procedure, you want to use a student's t-distribution and the type of test. What do I mean by that, the type of test? Good, right-tailed, left-tailed, or two-tailed. So I'm not going to write that. If you need to, you write that, okay? To find or estimate, but we're not going to estimate. We use the calculator to find the t value, right? Or the p, actually, is what I meant, our p value. To find the p value. Step 4, conclude the test. And that means what? How are we going to conclude the test? Good, thank you, Ben. We're going to reject or we're going to fail to reject. We reject when p is less than or equal to your level of significance. Good. We fail to reject if our p value is greater than. Good. All right, I'm not writing that either right there, but you can if you want to. And the last thing is always interpret your conclusion in the context of the application. Okay? Those are the 5 things. We've been doing that though pretty much the whole time. The first thing, you make sure it's a random sample, right? You state your level of significance, you state your hypotheses, your null and your alternate, then you set up your test statistic, you find your p-value, you conclude, and then you interpret. All right, so same basic steps as before. So I'm going to give you an example. Now, all I want you to do right now is to set up the null and alternate hypotheses, and then I'll show you how to actually do it. Did you notice in the t distribution, the test statistic uses r? That if you're first calculating r, then you're plugging it into that. You know, it's a whole lot of steps. So today, I'm just going to show you how to find your p-value, because that's what I think is more important. All right, because we've already calculated r, and please tell me you would be able to plug it into that formula. Nods of affirmation. Good. So if I asked you to do that on your test or your exam, you would be able to do that? Yes, you would. Don't you shake your head no. Yes, you would. Do you get the formula sheets? Yes, you get the formulas on the formula sheet. So yeah, you should be able to do it. All right. Have you ever heard the expression learn more, earn more?
No.
No?
Never.
Are you for real or facetious?
For real.
Oh. Learn more, earn more. Learn more, earn more. Most of the time they say you know, the more education you have, the higher pay and salary you're going to have. You've heard that? Okay, thank you. Maybe not said that way, but that's a short and sweet version. Learn more, earn more, okay? Which I cannot say. So we're going to test that. Let x equal the percentage of the population (25 or older) with at least 4 years of college. And we're going to let y equal the percentage growth in per capita so per capita income over the past 7 years. Do you understand what that's saying? People will look at the past 7 years, right? And then calculate how much their income has increased, the percentage that it's increased, okay? All right. So, using those X and Y's, a random sample of 6 communities in Ohio gave the following information. And this is collected from where? Hang on, I'll let you know for sure where it came from. Life in America's Small Cities, based on, or by G.S. Thomas. So this was really collected, okay? All right. So, following information. X, here's all of our X's, here's all of our Y's. The first X, 9.9. And it goes with 37.1, 11.4. It goes with 43.0, which is just 43. 8.1, 33.4. 14.7, and it goes with 47.1. 8.5, 26.5, and 12.6, which goes with 40.2. And we're going to set our levels of significance, or use a level of significance of 1%. So right now, I want you all, using that information, to set up the null and alternate hypothesis. And the information on the previous slide. You got it? You got it?
Something.
Okay, we should all be able to get the null. The null is what? What equals 0? Row. Good. Row equals 0, which means what?
Yes.
I'm not kidding. Which means what?
X and Y have no linear correlation.
Good. There's no linear correlation between the X and the Y. So, I want you, using this paragraph then, to be able to set up what you think we want to test. Do we want them to have a positive correlation, a negative correlation, or just or just make sure they're different, which is not equal to 0? Positive. Learn more, earn more. As X increases, which is a percentage of the population 25 or older with at least 4 years of college, we want the percentage growth in per capita income over the past 7 years to increase, because that would show, or we would think that as you learn more, you earn more, right? Good. I'm proud of y'all. So our alternate, I'm not being facetious here, I'm being for real. I'm proud of you. That's the hard part, is to figure out what are you testing, right? So we're testing, is that greater than 0? Is there a positive linear correlation? Okay? So to test this, we're actually going to calculate using our calculators. Make sure you have it out, okay?
I call that lazy.
So you're going to want to put X's in your L1 and Y's in your L2. Okay. Got it?
Oh, you are.
Does everyone have a calculator? Put your X's in L1 and your Y's in L2. If you're still typing on your calculator, I'm assuming you're still putting it in. So, everybody's done? Perfect. Now hit stat, arrow over to test, and you tell me which letter you think we're going to use, because you're arrowing down to the letters, right?
G.
G says Lynn, regress, T, I, and T for me. Is that what it says for you? Are we testing for an interval? Because that's what I and T means. Okay, F. F is linear regression t-test. Are we doing a t-test? Okay, calculating R, is that what you just said? Yes, I could make you calculate R, but I've already done that. So right now, this is going to find T for us, right? And our p-value. So you want to hit enter. Your X list is in L1, your Y list is in L2. Your frequency is 1. Do you see where it says beta and P? Hello? Do you see where it says beta and P? Okay, in a minute we're going to talk about inferences for the slope. So this is the same type of test that you would do, okay? So which one do I want to select? Where rho is not equal to 0, is less than 0, greater than? Greater than. So we're going to arrow over, hit enter, go down to calculate, and it gives you a lot of information. The first thing I want to point out, it says beta is greater than 0. So in a minute or later in class, if we don't get to it, if we don't get to an example, if I want you to test whether the slope is positive, boom, here it is. You want beta to be greater than 0. If you want to test to see if the slope is negative, beta is less than it. So it's the same test, okay? So we might not get to an example But you can set up your null where beta is equal to 0. Then you set up beta is greater than 0. That would be, I would want a positive slope. Okay? I just want to point out, it's the same test, everybody. It's right here. Okay. So do you see it gives me a t statistic of 3.841472695? If we calculated r, plugged it into the formula, that's what we would have got. Okay? So I could make you do that, but that would be a whole lot of computation because you first got to find r. All right? The next thing is p. So what does that p tell me? P is equal to 0.0092, and I could keep going 181636, but let me just stop there. So that's my p-value, right? Some other things, it has degrees of freedom equals 4, because how many data values do we have? 6. So that's going to show you it's n minus 2. It's 4. If you arrow down, what else do you notice? Gives me A and B, so I could get my linear regression from there. So if I make you calculate a linear regression, can you check your work? Yes, it's kind of nice. You can also do that in one of the other tests up above, one variable, remember? But this is nice. And then what else do you notice it gives you? R and R squared. So here's a way you can check that, okay? Kind of nice. And then I'm going to tell you what that S means in just a few seconds, okay? All right. So using our p-value, what can we conclude? Alpha would be, if we're using a 1% level of significance, thank you, Nick, 0.01. So if I want to compare my p to my alpha, you always do it in this order, PA. P goes first. 0.0092 compared to 0.01 is less than, which means we're going to what? Reject. We reject the null. So what does that mean? What did we show? Okay, think about what rho means, though. Rho is the linear relationship between x and y, right? Okay, so if rho is greater than 0, what's that tell you about the relationship? Positive, right? Okay, so, and then our x and our y, in this case, x was people 25 years or older with at least 4 years. Y was their income per capita, right? Increasing. Okay, so since we reject the null, I'm combining we and reject. Wowza. Woo! Since we reject, there we go. H sub O, the null, we can conclude that the population correlation coefficient is positive. So that's between our x and our y. I'm assuming y'all know that, but I'll write it between x and y, right? However, you need to be careful. However, oh my gosh. E-E-R, goodness, however, we did not show that an increase in education causes an increase in earnings or income. I'll put earnings. We just showed that it was a positive relationship between the two. You can't, though, just go straight to it and say, boom, because you learned more. But we did show there's a positive relationship, so what's that going to make your audience think if you can show that? That's what it's going to make them think, right? Okay, but you can't concretely say it. It's been that way pretty much all semester, though, right? We can show something, but we can't say necessarily that that's what it is, okay? Any questions on that? I'm not doing another example, because I feel like you can handle it. Okay, good. All right. So a couple more things. We have what's called the standard error of the estimate. Okay? It's kind of like standard deviation. Standard deviation takes every data value and the mean, and then finds the distance between the two. Then we add all those together, right? The sum of the squares, remember? The standard error of the estimate does the same thing, kind of, except it's now how far away the data value is from what we would estimate using y hat, okay? So we actually use the residual, which I defined for you the other day, remember? Okay. So the formula, or what it's going to be, the standard error, S sub E is equal to the square root of the sum of all your y squareds minus A times the sum of y, B times the sum of all xy. Those A's and B's and sum of x's and sum of y's and sum of y squared, those are all the same things you've been calculating, okay? And that's all being divided by n minus 2. So that's the formula. Your book gives it to you this way, using the residual, but we didn't actually calculate it using it that way. So these are equivalent, but we're going to use the first one. It's the sum of all y minus y hat squared divided by n minus 2. And you know what y hat is, that's a plus bx, okay? So we're not going to use that second formula, but that second formula, like I said, uses a residual, which is the difference between the actual data value and what you would get if you used the estimate, okay? All right. So I'm going to read this to you. Like, you write down whatever you need to make it make sense, okay? But this is about the standard error. The nearer the scattered points lie to the least squares line, the smaller S sub E will be. So the nearer they are to the line, the smaller S sub E is. All of the scattered points lie on the line if S sub E equals 0. Think about it. If the standard error of the estimates is 0, it means when you use y hat, exact value for y. So they're all going to lie on the line, okay? The larger S sub E becomes, the more scattered the points are. So small S sub E, closer to the line. When S sub E equals 0, they're all exactly on the line. And the larger S sub E, the more farther away from the line they are. All right? So the procedure for finding that, for finding S sub E, one, it has to be a random sample. That's always the rule. So X and Y come from a random sample, and N has to be greater than or equal to 3. Step 2 in the procedure, you want to find A and B. And you want to find Y hat, which is A plus BX. And step 3, compute S sub E. So again, you can calculate all those things, the A, the B, and you can plug into that formula, right? Do I need to do it with you, or you can do it? Everybody feels good about it? You literally just plug into this formula is the one we're gonna use in this class, okay? So a couple more things I'm gonna say. I already showed you where you can do the test statistic for B, beta, but I do want to tell you a couple things about it before you actually leave today. And then you'll have learned everything, which is kind of amazing, all right? Do you want to see if the population has a positive slope, a negative slope, or any difference? You don't care as long as it is different, okay? So why do we care? Inferences about the slope beta. The slope, or beta, the slope beta is very important because it measures the rate at which Y changes per unit change in X. So we can actually test, like I said, using the null of beta equals 0, which means there is no change, right? There is no change in the Y values as X changes. That's what it would mean, right? So there's another theorem, and then I'm going to let you go today after you write down the theorem, because you should be able to find the t value and the p value just like I showed you all ago using the same test, okay? Good. So the last thing is the last theorem. It's theorem 9.2, and it's about beta. Let B be the slope of the sample least squares line, which is y hat equals a plus bx, where n is greater than or equal to 3. Okay? And let beta be the slope of the population least squares line, which is y equals alpha plus beta x, which in theory is computed from the population of all x, y data pairs. And we let S sub E here, I need to make that E lower. S sub E be the standard error of standard error of the estimate computed from the sample. You realize, just like before, we use our sample to make inferences about our population. So clearly we have a sample, right? Then if we have the population beta, T is equal to beta, or excuse me, B minus beta divided by the standard error of the estimate, which is then divided by the square root of the sum of the x squareds minus 1 over n times the sum of all the x squared. And we have, for this t statistic, a degrees of freedom equal to n minus 2. So we can make inferences about it, okay, using a test of the null would be beta equals 0. If you want to see if there's a positive slope, you would do beta is greater than 0. If you want to see if there's a negative slope, you do beta is less than 0. And if you just want to test, is there a change in the y values of the x increases, you would just do beta not equal to 0, okay? But the test statistic, you use this to find it, so I don't feel like I should. If you want more information on finding it, it's on page 579. And it goes through an example, it walks you through it, okay? But I am going to give you some problems for this section, okay? Hello, you just use your calculator to find it. So the only thing you're really doing is having to set up the null and alternate hypotheses. You do have a test Thursday. Okay, so it's on chapter 10, which you already did the test review on, and if you haven't showed it to me, it's due Thursday. You have a test on chapter 10 and then chapter 9, which is section 1 through 3. We just did section 3 today. Yes, you have a test. I know, you're just messing with me, I know. Yes, you have a test, okay, chapter 10. Which was the chi-squared F distribution in ANOVA. And then chapter 9, which is there a linear correlation, right? Is it positive or negative? So that's finding R. Is there a strong relationship? That's the coefficient of determination. How close are the points fitting to the line? Finding the least squares line. And then today's, which was making inferences about the line, right? And then making inferences about beta. So can we make inferences about the strength of the relationship? So rho, okay? Thursday. Next Tuesday, we're doing an exam review. If you go to Bassett, you're staying after gum school, after you have some lunch, you're taking the exam. If you go to Magna Vista or Martinsville, your exam for me is that Monday, the 23rd. So Thursday, I will collect the test review I gave you, and then the few problems I'm going to give you to make sure you understood section 3. I am not giving you more problems on section 1 and 2. There's a test review at the end of chapter 9. If you'd like to work some more, go for it. This is a college level class, and in college, you're expected to work it if you want more practice, okay? Any questions for me? Promise you feel good about today's lesson? Don't just say it so you can get out of here. For real? All right, awesome. Have a great day.